big difference is in subtractive machining, the tool has to get in to the workpiece. In additive printing, because you're building up, you have access to the inside as well as the outside. So you can have things like axles and nested parts and overhangs that a subtractive tool can't get into, but that you can build up additively. Also, ideally, it's net shape. And so this is a link to, let's see, Ohad, are you on the call? Uh, Ohad uh, is one of the leads for Fab Labs in Israel. He also is a lead for education and research at Stratasys. And this is a curriculum he developed about 3D printing. Uh, there are multiple reasons to 3D print. This is just a link to a designer who's been working on 3D printing turbines and motors and clocks as examples of his work. One of the motivations to 3D print as a process is complexity. It essentially is the same amount of work for the printer to make just a solid volume or a dense structure full of geometrical information, that there's really no cost difference to make something more complex compared to something simple. One is you can get access to print things that you couldn't get to with a subtractive tool, like if you look in this clock into the springs in the mechanism or the bearings. And then one of the motivations ideally is that this is net shape, meaning you don't have a lot of waste produced. You just produce the part you want. That's not quite right, because most of these processes do need extra material, but ideally there's less waste produced in an additive than a subtractive process. On the other hand, there are many constraints. So 3D Benchy is a classic test part, and I'll talk a lot about test parts. There's many constraints in 3D printing. It's not remotely magic. You don't get to just push go and have parts magically come out. So one constraint is these are greatest hits of failed 3D prints. You can get the job running and you come back, and for an extrusion, you get a tangle of spaghetti. For a particle binding, you get delamination. For a resin one, you get just goo. There's a range of ways that the printing process can fail. There's limits on the resolution you can achieve depending on the process you're using. Generally, printing is slow. Most anything interesting you want to do takes hours, not minutes. Depending on which material you're using, it can be very expensive, hundreds of dollars to produce small parts, depending on the material. You can't print anything. There's a subset of materials. So we'll make a lot of use, and I think yeah, do I talk more about this? No, I don't. So let me talk about it here. PLA is polylactic acid. It's a plant-based polymer. So even though it looks like plastic, it comes from plants, and it actually locks up carbon in it. In a sense, it's carbon negative. You use more carbon to print it than it uses. So that's a friendly material. These are other polymers you can print. Sorry, I'm just realizing. Okay, I will come to that. Uh, um, so a number of the materials you print are petrochemicals that are less friendly for the environment, and there's a range of materials you just can't print. Another issue in printing is it's not harmless. So depending on let's see, there's a question about recycling PLA. There's a number of projects uh, like this one that work on making machines to recycle plastics. Um, it's promising, but the performance isn't as good as the original source material. So for the most common process you'll use, and I'll talk more about these, FDM, the FDM process creates volatile materials and it creates ultrafine particles. And depending on what you're printing and how much you're printing, those are hazardous. So this is a good study of it. The upshot of it is PLA is fairly friendly. The volatile emission is low and the particulate emission is low. The other kinds of polymers are much nastier to be around. And so a little bit like soldering, it's not a hazard just to be next to it, but you shouldn't sit next to it for extended periods. You should use the machine in a well-ventilated environment. Then, so Marty, the link I just showed you this is a good study on it. And again, the conclusion is PLA is comparable to background chemical emission. It's fairly well behaved. The other polymers are more serious. And this paper is a good study on that. I see there's a notion about precious plastic. Please do document that and share it next week if you built that, Kataya. So one of the biggest limitations of 3D printing is design rules. And to print successfully, you need to be aware of the design rules and design around them. There's many different test parts. What I've linked here is a series of FreeCAD files and STL files, each testing a design rule. So this first one is the thickness that I'll cover a number of processes. These apply to all of them. Here, this was done on an FDM printer. So the FDM printer lays down a pass of a filament, and the thinnest wall could be a single bead, but that has terrible structural integrity, then two, then three. So one design rule is how thin a wall can be before it falls apart. And then in the opposite direction, I've made a gap. And there's a limitation for how close the gap can be before it fuses. The next one is in those parts, there's a part around an axle, and in steps, I'm making it smaller and smaller. And the question is how close it can be while you can still rotate it. And so all of those released, those parts didn't release. This next one is the angle. And so what this one is doing is when you build vertically, you just build vertically. As you start building horizontally, when you start making paths, there's an angle where each one can overhang the one before it. And sorry, that was the wrong tab, this tab. And so eventually, as the angle gets steeper and steeper, it gets worse and worse. As the printers have improved, this has gotten much better. And so you'll see already at about 10 or 20 degrees, it's handling the overhang. And this has gotten better over the years as the printers have improved. This one is testing how far a horizontal overhang can go before it fails. And you'll see there's a very short distance before you just get spaghetti underneath. This one is really surprising until you do it. The one I just showed is you first build up, then you just go straight out. And so you can't go very far. But a really surprising one is bridging. So if you build up in layers, posts, then you try to go from here over to here. Here you go to here and you stop. And so it's just free in space. Here, the nozzle extruding the filament pulls it over here and anchors it there. And so when you're bridging, you'll see you can go much further and you can pull over a space and attach it. This one is the strongest part, fills material everywhere, but that's the heaviest and takes the longest time. You can save mass and save time by reducing the density, although that makes the part weaker. Then any of these printers have supports. And so if you need a long overhang like this, you have to build with the support material and remove it. And a lot of the effort in using the printer is how do you get the support material out? And different printers have different approaches for that. As much as possible, it's a great idea to avoid supports. And so as long as you're bridging, or as long as the angle has enough of an angle, you can design around not needing supports. Then most of these are anisotropic. So in this part, on this beam, the filaments go that way. On this beam, they go this way. And so if you pull in tension in that direction, you're pulling in the long axis of the filaments where they're stronger. If you pull in this direction, you're pulling where they're bound, and that'll fail more easily in that direction. This one is showing the apparent surface finish is a strong function of the angle of the print, where the steps are more noticeable here. And then this one is printing a part with a designed outer and inner dimension. And if you actually measure it, there can be quite a difference between the actual dimension you get and the dimension you thought you get. And it can be difference in an outer and an inner dimension. So each of those are design rules, and they have many implications. So one example is you don't design a part with a sharp corner like that, because you'd have 3 filaments here and then 2 filaments here and only 1 filament here, and you'd get a tangled mess there. And so you want to design it with something like that, so there's a solid ending. You don't want to design walls that are too thin. You don't want walls that are too close. You don't want to go out over an overhang and stop. You either want to bridge between supports or have a slope. All of those go into, sorry, wrong tab again, all go into design rules. So you design your part around the limitations of the printer. And so you don't design it in a vacuum, you design it around knowing your printer. And so the first assignment is to test the design rules. So how skinny can a wall be? How small can a gap be? How close do you need to be to release it? What angle can you print? How do the dimensions of the printer coming out relate to the dimensions you set to it? So characterize the design rules of the printer and then use those design rules in your design process. Once you're done, there's a range of types of post-processing. So this is an example of, for FDM, you have beads of filament. So this is an example of a material from Smooth-On that's designed to make a smooth surface from the slightly rougher printed surface. Each sort of printing process has some kind of post-processing to go with it. So for printer types, Shapeways is a vendor, and they maintain a good catalog of types of printers. The original process is from 3D Systems is stereolithography. Stereolithography uses a laser and cures a resin. And the here, let me add one more link. Stereolithography makes the highest resolution parts because it's down to the resolution of the laser, so it goes down to millionths of a meter. But the limitation in stereolithography is it has to be a resin that the laser can fuse, and when it comes out, it's a gooey mess, and you have to do a fair amount to clean up the part. But generally, that's used for highest resolution. FDM is where you extrude a filament. That was invented by Stratasys. Well, it's been invented to some degree multiple times, but Stratasys is one of the, Scott Crump is credited as one of the inventors. FDM makes parts with good structural properties, and the printers are now very cheap and easily hacked, and that's by far the most common one that you'll be using. You can also extrude other materials. This is a colleague at Berkeley who extrudes clay. And so instead of extruding plastic, he uses printers that extrude clay and ceramics to make these sort of beautiful objects. This is a colleague at University of Southern California, and oh, his site is down. Uh, what he does is, so let's see, looks like that link moved. He prints concrete. And the way he does that is it's like a 3D printer, and he's pumping out a very thick kind of concrete paste. But the crucial thing he does is rather than just extruding instead of just having a nozzle that extrudes a filament, in doing this, because he needs to move much more material, he extrudes a thicker section, and then he has a programmable trowel, and this thing can control the angle. And so what it does is you extrude it, and then that sets the angle of the surface. And by doing that, you can move much more material much more quickly to do large scale, concrete scale printing. Let's see, this was Z Corp, spun off by MIT, bought by then 3D Systems. This is where you print and ink, and you use it to fuse a powder. The strength of that one is you can print at printing resolution, and you can print in color. The weakness is it makes weakly bound powder, and so it has poor structural properties. You later need to infuse it to strengthen it. Polyjet, which came from Objet, now merged with Stratasys. Its inkjet prints the same kind of resin used in STL or similar, but it does it with a print head and little droplets and fuses those droplets as it goes. So these are much more expensive machines. These machines can cost hundreds of thousands of dollars. But this is a nice process to print functional prints that have many different kinds of materials. So you can vary over it the material properties, you can vary the color. And so that's been the nicest process for multi-material printing. This is an odd sort of quirky one. This is one where you print on paper, cut out the sheets, and laminate it. And so it makes beautiful colored objects. They have poor mechanical properties. Then selective laser sintering. Oh, sorry. Yeah, I'll go back to show you. Selective laser sintering is where you spread a powder, and then you use a laser to sinter it, and then another layer, and then sinter it. One of the strengths of this is you can do it with metal, although that needs a $100,000 machine. And one is it's a really interesting one for the supports. So yeah, let me go back and show that. There's a really interesting group called Nervous Systems. And this was a project they did to make a dress in a laser sinter process. And so to make the dress, they did this beautiful mathematical job where here's the dress. And then mathematically, you drop the dress into the build volume. Keeping mathematically a little bit of distance between each part of it. So you let the whole thing fall in. Again, not physically, but mathematically. Then you send that to the laser sinter machine. And then here's the beautiful thing. When you make it on the laser sinter machine, what it then does is where the laser fuses it, it's fused. Where it doesn't fuse it, the powder is still there. And so as you're building, the powder kind of automatically supports it. And then when you're done, you just reach in and shake it and pull it out. And you get this beautiful, intricate mesh dress that in other printing processes would be miserable to do, to separate all the support material. But here, the support material is just the powder bed. Another example is this was a student in the How to Make class at MIT, and he wanted to see how far he could take FDM printing without supports. And so he tuned all the parameters to come up with this really interesting regime where this whole thing is printed without support material anywhere, just by tuning the FDM bridging and sloping to be able to pull it out. This is a process aiming to control the ambient environment to build faster and to print a green part that you then fuse. This is the highest resolution. So Nanoscribe makes printers that print down to nanoscale resolution. They make nanostructures. And the way they do that is it's with a 2-photon process. So stereolithography focuses a laser, and at the focus of the laser beam fuses the material. In a 2-photon, and then in a 2-photon process, you have 2 laser beams, and physically, you need the energy from one combined with the energy of another to make the chemical reaction. And so the reaction happens where both beams are, and that gives you a significant resolution enhancement. So this is limited. The biggest part you can make is down to millimeters, but it lets you make micron scale parts to print the very tiniest parts that way. And then this is a link to a meeting I ran a few years back, and there's a lot of updates following that on the idea of digital printing, not by printing and cutting, but by doing microassembly and disassembly. And so let's see, I'll add an update to that link. This was one of my students who developed a machine that's a cross between a 3D printer and a pick and place. So rather than printing or cutting, it's assembling little tiny parts, and it's using that to make micro robotic systems. So I'll add a link to that. So those are the most common processes. And then in the machines, Make Magazine periodically does a shootout to compare all of these printers. Adrian Boyer is a colleague who started RepRap. And he started RepRap less so just to make printers. He was really driven by the beautiful question of self-reproduction, of how close can you come to a machine that can make its own parts. RepRap inspired multiple projects. So Ultimaker grew out of a fab lab in Utrecht. They focused on print speed, reducing the moving mass to be able to print as fast as possible. And an offshoot of that was a lovely project where Uris, let's find a video. See if this is what I want. What Uris did, oh, I have to wait for the Michael Bloomberg ad. It's election season here. So, let's see, is this what I want? Oh no, sorry. That wasn't a good use of your time. That was the little elephant. I want the big elephant. Okay, so what you're looking at here is they put Ultimakers on a gantry, so the printer can print much bigger than its own volume. And so all of these Ultimakers are rising, printing these columns, and then they would pull each column out. And then they did this tour de force project where they made a full-size elephant by printing it. And then MakerBot descended from RepRap, also started as an open source project, somewhat controversially became closed source, was then sold to Stratasys. And we'll re-meet Blair, who is behind that, when we get to more machine building. Josef Prusa, again, built on that history, and Prusa's done a really good job of just stabilizing a best practice design and optimizing the design so you have very fine control over everything within it. And so Prusas have been doing really well. They have an upgrade that lets you feed multiple materials at once into it. So it's a nice open source design, but you buy commercially, and it gives you really good low-level control. In a slightly different direction, Sindo is a company that historically made print engines for 2D copiers, and they looked at 3D printing and saw how weak many of the designs were. And so the Sindo is, they significantly cost reduced it. It cost around the same as a Prusa, but the difference is everything is optimized to need as little attention as possible. So you put in material in a cartridge, it adjusts just about everything. And so it's designed to be very user-friendly and not need much tweaking. So it's good for a kind of a beginner or unattended machine. You don't have as much low-level control as you do on the machine like the Prusa. Okay, yeah, I'll talk about print farms later. Then my students started Formlabs, and what they wanted to do was bring resolution to the masses. So the Formlabs machine is based on stereolithography. They have a wide material set, but they did a lot of work pushing the resolution. So the typical road size in an FDM printer is 10,000ths of an inch. A mil is 25 microns. The Form 3 prints down to 1,000ths of an inch, 25 microns. So much, much, much higher resolution in a few $1,000 machine. Objet machines, again, are much more expensive, but are nice for printing multiple machines at once. There have been a number of versions of 3D printers made in the machine building projects. We'll be seeing that when we get to machine building. And then here's the link. I'll need to fix this link for Precious Plastics, which is how to make recycling machines. I'll go back and fix that link. So those are some of the notable machines. Most likely you'll be using in most of your labs an FDM style machine. Then, given the popularity and the maturation of the FDM machine, these are all interesting. These are vendors of filaments, and all of them have really exploded. And so let me grab this is one of my favorite ones. Let's see if I can find it easily. Yeah, let's see, that isn't, let's see. Sorry, let's try, let me try one more time. Oh, timberfill. I was searching for the wrong thing. So this is a really surprising one. The part looks and feels like a wooden part. It's wood fiber in a biopolymer matrix. And so the filament looks and feels like sticks almost, but when you extrude it, it flows. And it's clearly not just wood that was machined from a tree, but it doesn't look and feel like a piece of plastic. It looks and feels like wood. And so there are filaments from these vendors that are metal filled. Sorry, it's not, the metal filled isn't metal. It's not a strong metal part, but it looks and feels metallic. There's ones that do have conductivity. There's ones that have carbon fiber, which isn't as strong as long carbon fiber, but is stronger. There's ones that sparkle. There's ones that are bendy and are flexible. All of these need a lot of tuning. And things like the metal filled ones also are tough on the printer, and you can need to lubricate and strengthen the guides for it. But once you tune them, these have been really expanding. And so they let you make things you can see through. They let you make things that are bendy. There's a much wider range of these filaments maturing now. Then for printing, Prusa makes many of its own parts on its own printers. So they've got this room of 300 printers. In my lab, I have a farm of maybe 15 of them. And I really recommend this, that the printers have come down to at the low end, a few $100s. And once you have a farm of 10 or tens of them, you use them differently. Any one job takes hours, but the net throughput of a print farm is 10 or more times bigger. And so there are many jobs you'll send to a print farm you won't send if you just have one printer. And so Prusa, for example, has come out with a really low cost model cut way down, the mini, and uh, the kit version of it is just $300. And so for a few $1,000s, you can set up a farm of 10 of them. And it really does change how you use the printers. I recommend that. Shapeways, I mentioned, is a good vendor that keeps one of almost every printer. You can send the jobs to them. It's much more expensive than you doing it, but there's many printers you couldn't afford to do. These are all service bureaus where you send your job to it and it prints it. Mainly that's for printers you couldn't afford to do. This is a company I work with that does aerospace, and metal 3D printing is so important to them. They ended up buying out their vendors, and they manage this farm of laser metal center printers. And each of these are $1 million class machines, and you need to carefully control the environment. And each machine needs a support person that goes with it, but for metal printing. One of the things that is emerging is there's a couple startups that are working on extruding metal filament and melting it while you extrude it to do FDM metal, and those are coming. Crunch Lab is asking about Creality. I don't know anything about that. How does Creality differ? Don't know anything about it. Dan says he has a farm of 15 flash form. Dan, talk about running the farm if you're on.
I'm muting now. Can you hear me?
Yeah, yep, it's good.
Yeah, so we have a farm of 15 flash forward finders, which I think are made in the same factory as the Syndos. There's like one big factory in China, I heard. I'm not sure if that's right. But we run those every day of the year, except for the 2 days the museum's closed. We have 3D printing workshops, and they're really reliable. The Syndo is really good too. It seems similar to that, but it's $300, and we can buy a lot of them for that price. And we have over 60 Flash Forge machines at this time. So we have multiple farms of 15 to 20 each in each
Yeah,
farm.
that's great. And again, it really changes how you use it. Once you have that just volume capacity, even though any print is low, the the people throughput goes up significantly.
Yeah, each person has, for our workshops, we need to finish it in an hour. So each person has to have their own 3D printer to enjoy the rest of the museum. And for students, they can mass produce stuff much quicker. Yeah, it changes everything once you have multiple machines.
Yeah, and then while we're on print farms, I'll talk more about software, but Octoprint is a lovely project that runs on a Raspberry Pi. And what it does is it takes a G-code style printer and provides a remote web interface. And so the way I run our farm is each printer gets a Raspberry Pi, and then the cloud interface is each one is running Octoprint that lets you run them all over the network. Okay, so that's print farms. Now we come up to files. So you need to produce a file to go to the printer. Stl File Format is the most common. It stands for stereolithography. It dates back to 3D systems. Its strength and weaknesses is how dumb it is. So all there is in an STL file is a list of triangles. That's all it is. And so there's never any issue with interpreting it. It's just triangles. There's a couple problems with STLs. So one problem with STL is you have a beautiful flowing design and you're going to turn it into a mesh of a bunch of little triangles. So you lose design information. When you do it, the files can be huge. So this week, you should link your design files, but generally don't link your STL files um, unless they're small, because you can easily have gigabyte STL files for a really big mesh. Another problem with STL is, bizarrely, it doesn't have units. So you need to interpret the file to get the right units. It doesn't say what its units are, it's just numbers. Another problem is it doesn't let you specify color or material properties. It's just triangles. Nevertheless, it's the most common format. And an important thing to know about STL is it's a really easy format. You can do it in ASCII, but that's almost never done because they're much larger. You write it as a binary file, and it's really easy to write a program to generate STL. And so if you like programming, rather than using a CAD tool and then a meshing tool, you can just write programs for algorithmic designs to write your own STL files from scratch. So that's most common. PLY is a simple extension of STL that came out of a Stanford scanning project to represent color as well as triangles. Then this is a bit of a mess. One of the leads on this has been a colleague, Hod Lipson, to come up with a standard for what comes after STL, and it went from AMF to 3MF. It's a specification to deal with what follows STL. The problem with it is there's many different directions you can go in to improve STL, and this one kind of did all of them. It didn't pick a winner. It's just kind of all of them is possible. And so one of the possibilities is to use a functional representation where you represent interiors rather than exteriors. And so it's a big kind of unsettled standard. It's emerging, but hasn't gotten great traction. On the other hand, OBJ is a nice format that came from Alias, now Autodesk, as a CAD file format, but it nicely represents color and geometry and assembly. And that's been emerging. It wasn't designed to be a standard, but that's been emerging as a nice format you can use to represent those properties in printers. Likewise, Vermal and its successor X3D were created for doing 3D graphics online. And those are increasingly also used as interchange formats to go to printers. Once again, color in particular for that. Part of AMF is being able to use volume. So this is a thesis on, I talked about this in the CAD week. Instead of representing patches of a surface, you actually, it's crazy, 3D printers represent surfaces, not interiors. Emerging is to be able to use a functional representation to actually represent the interior. And I'll come back to that in scanning. Some printers actually let you, instead of sending triangles to it, actually send voxels. Get raw access to have voxel level control for really complex geometry. And then most in particular of the DIY style printers use G codes, which again is an ancient format, but a commonly supported one. One of the interesting things about using G codes is normally in 3D printing, you print on layers, but the G codes can go in any axis. And so there's interesting experimental work with printing objects, not just by printing horizontally, but by using all three axes to make smoother surfaces and print more quickly. That's not yet well supported in the software workflows, but the G code can support it. So software. You design your object for this week, whatever it is you want to make. Most of the printers work in layers, and so you need to slice it. So you need to make the layers. You need to figure out where you need the supports. And then within the layers, you want to draw the outsides and the insides and then fill in the interior. So that's the job of the slicing. So the first step is you'll need one of these programs. These are mesh manipulation programs. And so this one is commercial. Mesh Mixer is free. NetFab, MeshLab is an open source one. What these let you do is deal with meshes. You may have a mesh that's too dense and you need to downsample it. It may have glitches you need to smooth. You may have holes you need to fill in. You may need to cut off parts of it. And so think of this as like a like GIMP, but for meshes. So and it's also just good for viewing and characterizing. So you need those to look at the mesh. Then there's a number of these. Let's see. I just muted everyone. Unmute if you do mean to talk. So Replicator is one, Skyforge is one, Slicer is one, Cura is one, Ice SL is one. All of these have matured and largely can do the same thing now. They take your job, they slice it in layers, they do the infill to vary the density. They figure out where you need supports. They figure out the strategy for the path, and then they prepare the file to send it out. There's a slight controversy. Prusa has forked Slicer. They're improving it in various ways. There's a little bit of tension because there's two kind of parallel tracks. At some point, they'll merge together. But so all of those are to slice your file. Then print run is a nice project to provide an interface to a G code to send the file to it. And then I mentioned Octoprint. Octoprint is a layer above that. It provides an interface to the machine. You don't really need this for one machine, but this is great when you have a farm of machines. You put a little Raspberry Pi next to it and you use it to run them as a family. Then finally, Sketchfab and Thingiverse are both platforms you can use to share your projects. But the other thing both of them do is they have plugins that are designed to make it easy to view your model. And so you can use their plugin. Let's see, this one is just a gallery. You can use their plugin. Okay, this one is the 3D one, where in a web page, the plugin loads, and then with that, you can navigate and look at the model. And so you don't need to write this. You can use their plugin to have an interactive version of your model on your site. So for printing, the assignment is to you design it, 3D print an object. The object should be small, just a few centimeters, because you're going to be limited by machine time this week. And key is it has to be something that can't be made by a subtractive milling machine. So it has to have nested parts, overhanging parts, shells of parts, meshes. There have to be features that require building it additively that you couldn't build subtractively. Last part today is scanning. So printing is the data becomes the thing. Excuse me, scanning is how the thing becomes data. So you have an object and you're going to bring it into the computer. Scanning is frustrating. There's no magic bullet. Typically, you start with the object, however it is you scan it. Not all, but most scanners end up with a cloud of points, just points in space. Then typically you have to triangulate that. So you have to make a mesh out of it. Often the mesh has holes where the scanner didn't see anything. Those meshes means the print will fail. So you need to make it watertight, closing the holes. And then often you want to texture it with the color of the image. So one of the machines in my lab at MIT is one of these. These cost $1 million. They do math that's called the radon transform that I explain in this class. And what they let you do is this. This is a housefly. So there's a housefly. And this is now a fly through of the head of the housefly. So the CT machine scans the inside as well as the outside. And it does it down to a resolution of millionths of a meter. So that's the best of all scanning tools, but it cost $1 million. There's work now, there's a few efforts to try to bring this down to make more accessible X-ray 3D scanning. Then this is a scanning tool that can see down to individual atoms. And so it works by scanning a probe and measuring height. You can do this much more coarsely, but the great strength of this is you can do it down to extremely fine resolution. Confocal microscopes are heavily used in biology, but have a role in rapid prototyping. What those do is you focus a laser beam. And so this is the beam coming in. And then either in reflection or transmission, you then have an imager looking at it, and the imager is focused to the same place. And so it's confocal. Then what you do is you move that focal volume in all three axes. And so you 3D scan an object by moving the confocal volume. And so that lets you do 3D scanning optically rather than with X-rays. You can scan by selectively slicing the object, and you slice it away to see what's inside. And that's done, for example, to reconstruct neural wiring. A version of that is what's called the milk scanner, where if you take an object and you pour an opaque liquid over it, like milk, you can watch the object disappear into the liquid and watching it disappear gives you a boundary that's a 3D scan of the object. Digitizers are surprisingly interesting and useful. So if you look at this is a building Frank Gehry designed at MIT that's crazy looking. And the design process for his buildings start not in a computer, but with materials. He'll like cut and fold paper and make materials to make the shape. And then rather than digitizing it the whole side, you don't need to digitize everything. What you want to do is digitize the important features. Where are the boundaries and where are the corners? And so these arms, you have a button with your finger or a foot pedal, and you touch it to points, and it measures where you are. And so you add value because by choosing where you digitize, you're getting a very clean scan because you're picking what points to measure for that. So those are digitizers. Lasers, scanners. This is a state-of-the-art one. This one costs $25,000. What those do is you have a source that bounces a laser off the object, and then separated from the source, you look at it and you see where the light came back. And so by measuring where the laser beam went, by where you saw it, these scanners have a separation between the laser source and the laser imager. And so state-of-the-art for these are near real time. And this is a very impressive one that has a graphical processing unit in it. So it reconstructs it right on the scanner. This was a project to make a open source laser scanner, Fab scanner, but using the same principle. So these can be very high resolution scans, and they can range from little to big objects. The biggest problem with these is if the surface is fuzzy, it can absorb it and light doesn't come back. Or if it's shiny, it can bounce off and go away from you and doesn't come back. So you may or may not see the light come back. But these can be among the fastest and highest resolution. Lidar is where you send out a laser beam and you measure the time for it to come back to you. So those are used for things like self-driving cars, and those have been coming down in cost. They're not very high resolution, very close in, because that needs very tight time resolution. These are great for very large scans. If you want to like scan a building, things very macroscopic. This is a scanner that uses an array of emitters and then detects it with that. That's a cheap, easy one. Then this is very much a work in progress. This area, these keep getting designed, redesigned, bought, maturing. What these do is really interesting. So in a normal camera, you have pixels and just light comes into the camera. What these ones do is each pixel in the camera is actually like almost like a radio. And so the light you send out, light is a wave, but you put a wave on the wave, a modulation. It bounces off of the object. The light comes back in. And each pixel, in addition to measuring the intensity of the light, also measures the modulation. It measures the phase of the light. And by measuring the phase of the light, it lets you measure distance. And so it's a camera that sees distance as well as intensity. And these are becoming really important for augmented reality. So in augmented reality, you visualize things that aren't there. And to do that, you need to know what is there. And so there's a big push to develop these time of flight optical sensors and put them in phones. And so phones are emerging, and there's a lot of work on this in the development pipelines to make phones that have time of flight sensors. And so those are going to be coming increasingly I think the driver for 3D scanning. Then you can scan with vision systems. And so this is a Intel kit for doing that. And then finally, we now come to photogrammetry. So photogrammetry is, this is an open source photogrammetry kit. And then these are many, many different versions of photogrammetry systems. And let's see that one. Mesh room is an interesting one. CallMap is an interesting one. What all of these photogrammetry systems do is you have an object you want to scan, and you just take lots of pictures, and you typically take them in just random locations, and each picture is only one view. But when you take the data set of all of the pictures, you then solve a hard math problem to ask what object is consistent with all of those pictures. And so the strength of this is you don't need any special hardware. You can just take your cell phone and take a whole bunch of pictures. Then you run it through a lot of math. It eats all of that and then produces the scan. So this is convenient. You don't need any special hardware, and it can produce beautiful scans. The issues with this, one is it's not metrology. It'll produce a scan. The scan is its interpretation of the pictures, but it may or may not be correct. So it may look like your object. It may differ a little bit from your object. The fidelity varies quite a bit. And it's very easy for it to fail. If there's too little background, it has a hard time figuring out how to reconstruct it. If there's too much background, the background confuses it. These help if there's just enough background that the visual field helps it do the reconstruction, but getting that right is an important thing to do it. So these are very much evolving. You can see from this list, there's lots of them and they keep changing. But this is a way you can just 3D scan with a phone. Then this is a patent on speckle scanning. And there are a number of versions of this. The current version of this I like is, oh yeah, Stl is noting photogrammetry, of course. Most of these you get the texture. Most of these scanners now do the texture. So the 3D Sense from 3D Systems, what that one does is it's a combination of these. Let's see, I'm not sure if, well, actually, I have one, sorry. No, I don't have it out right now. I won't take the time. So the 3D Systems Sense looks like this. And so what it's doing is it's different than the laser scanner. So the emitter is putting out a speckle pattern. The speckle pattern is like random dots. And then the camera is looking at the speckle pattern. And so you do photogrammetry. As you move it, it's taking pictures. But the difference, excuse me, here is at the same time it's taking the pictures, it knows about the speckle pattern going out to illuminate it. So it's taking pictures of the object with the speckle it's putting on it. And that gives it much more mathematical information to do the reconstruction. And so compared to ordinary photogrammetry, by putting the light out that way, it's easier to use, it's faster, and it's more robust. And so this is something that I like as the easiest entry-level, quick, easy-to-use scanner. These are down to a few $100s for these speckle-based scanners. Then related to that is the idea of structured light. And so in structured light, you can do it with a video projector, but what's neat is you can get little laser projectors. And these are video projectors, but unlike the normal video projector, because it's a laser, there's no focus. So the beam is always in focus wherever you aim it. And so this is an example of, a while back, a simple example I did of structured light scanning, where the projector is putting a series of lines out and changing the line resolution. And so if you look at the person, you'll see you put out the pattern of lines, and then the bending of the lines is what's giving you the depth information. And then you can combine all of that and turn that into a 3D scan. And again, the difference here is, unlike photogrammetry, you're controlling the light out as well as the light in, so you get much more information from that. And then we get to the most interesting scanning, and this is what I was alluding to before. So Paul Debevec is a colleague at USC, and in doing this light scanning, sorry, I want to find, he has a nice example. He's updated this since I last looked at it. Okay, good. No, that is here. So to explain this, this is very different from any of the other kinds of scanning. The way it works is you have the object you want to scan, and what you want to do is be able to send light in from every direction, and you want to be able to image from every direction. And so what's happening is, if you look at the surface, there's light that bounces off of the surface. There's light that, instead of bouncing at one angle, gets scattered in many angles. There's light that goes into the surface and comes back out. All of that goes into what's called the BRDF, that characterizes all of the properties. And so, for example, shiny surfaces are hard to 3D scan because the light doesn't come back to the scanner, even though they're very reflective. So, okay, so I'm going to show you two examples from Paul. So this one is a lovely project he did, where the way he's going to do it is, he has a group of cameras. He has an arm where he can control the light around the arm. And then here he's going to put in shiny glasses that are very hard for an optical scanner. Then Paul is going to spin this around, and he's going to put out what are called spherical harmonics. And the spherical harmonics are going to illuminate the volume around this object with every possible kind of light pattern. And then he gets these series of images of the spherical harmonic. Then mathematically, you take those images and you need to calculate the reflection fields. And so here are the views. And now comes a really interesting thing. He can separate the diffuse scattering from the specular scattering. He can find the normals, the directions, the roughness, and these are all the things you need to do to make a complete computer graphic model. And then you can merge all of those together and you get the geometry, and then you get the optical properties. And one of Paul's nice points are, even if you don't think you need to measure that other stuff, if you don't measure them, you'll get the geometry wrong because you'll confuse the optical properties with the geometry. And so now this is now computer graphics, and he's re-rendering it from doing that scanning. So some of the neat projects he's done, notably at the White House Maker Faire, a couple people on this call, we were all part of it. Here he's taking President Obama, and they made a light stage in the White House, so you can see all the cameras and all the emitters. And he's producing the data set. And then once you do that, you have a digital version of Obama. And this was very sensitive because of the next thing I'm going to show you. So Paul did that with an actress, Amy. So here she is in the late stage being scanned. Then once you do that, let me get to the, okay. So here's Amy, but this isn't her. This is the computer version of her. And then I think he does that. Yeah. Okay, so right now you're listening here. Let me come back a little bit.
We specialize in high quality facial animation for video games and films.
So you're not looking at her, you're looking at the re-rendering of her once you get the light stage data. And so that's a completely synthetic, and now that's the real her. And so doing this with Obama was sensitive because you can make a synthetic Obama who could say whatever you want. And so just handling of the data was a very sensitive issue. So light stages are the real state of the art in scanning. If you're interested, a really ambitious project is to make your own late stage to be able to illuminate an image from every direction. And finally, SLAM is simultaneous localization and mapping. And this is what you need for augmented reality. And this is the idea that rather than scanning an object, you want to be continuously scanning and building a dynamic version of the world that you're in. And so this is a library, Google's version of a library to be able to support that. So this is 3D scanning, but it's 3D scanning designed to run in real time in an ever-changing environment. And so it includes 3D scanning as a subset of even more capability. So the scanning assignment is scan an object and optionally print it. It's non-trivial to print a scan. You don't have to connect them, but that's something that you could do. Now I'm looking at the questions. Let's see, Argon. Let me remind. Okay, so there's a question from Luis. TomoPi is a tomography platform, among others, that Argonne National Lab has helped develop. And what this does is it's a whole pipeline to start from images, not of the surface, but tomographic images that project through an object and do the 3D reconstruction. So if you're getting X-ray data, this is an open source tomographic reconstruction pipeline. So that's types of printing, file formats, software tools, and types of scanning. Any final questions or comments? Bahrain, your hand up. Let's see, Saul, you're asking about making Play-Doh. Just explain the question. Why do you want to do that?
for my project, I want to do an ergonomic keyboard, so I want to shape stuff by hand to get the shape right, and then to scan that.
Yeah. So
and right now
yeah.
we're not on the lab.
Yeah, you'll find this is a classic kitchen project. You'll find endless recipes as kitchen chemistry to make your own Play-Doh as just a cooking project. That's a really easy thing to do. Other questions or comments? Let's see, Marty is looking at software. Nice. Marty's developed a workflow to go from the scans to the printing. Right, matrix scanning. Okay. Any other questions or comments? If not, the printing part of this week is going to be rate limited by time on your printers. So be modest because you're going to be limited by printer time, and try to get the throughput onto your printers. And then scanning will really be limited by just there is no single best solution, the proliferation. Experiment with all of these. And then this is a fun week. This is a creative week for what you design. And it's also a very interesting week for the range of printers and range of scanners we use. And so we'll do a tour of all of those next week. Again, we do have a Recitation Monday. They're optional, but encouraged. This one is going to be about disabilities, abilities, and assistive technology. And happy printing. This is a very creative week. Next week is a less creative week, but a really important one. Next week, we'll start electronic design tools. So happy printing, and I'll see you on Monday. Bye-bye.
Bye-bye. Ciao.
Bye.
Bye.